Hello, Bailey and Allie. It's Tuesday morning, so you get to start class on this video. I want you to begin today. I'll look at the homework and collect some other things from you when I get in a bit. But for now, if you could write down this example problem, and here we have a bicycle, a bicyclist, and his time is 0 seconds, 2, 4, 6, 8, 10, and 12. So if you would jot down this little chart, and the velocity of the bicyclist at 0 seconds is 0, 2 seconds is 6 feet per second, and so on. So there's the information for the bicyclist. So you can stop the video and write down the chart if you can't get it down quick enough. We're going to go ahead and graph this information and answer the question, find the distance traveled during those first 12 seconds, and we're going to use right rectangles in order to do that. So to use the right rectangles, we need a graph. So I'm going to put in 0 seconds, 2, 4, 6, 8, 10, and 12 seconds. At 0, he travels 0. At 2 seconds, he travels 6. So I'll call that the point 2, 6. And then the next one, at 4 seconds, so this is 2, 4 seconds, he travels 7.5. So I'll say 4, 7.5. And then at 6 seconds, he travels 8.5. These little numbers, I'm not sure will show up in your video, but I'm reading them to you. 8, he'll travel 9. So the point 8 over 9 up is on the graph. At 10 seconds, he's 9.5. And at 12 seconds, so we're 8, 10, last one, 12 seconds, he's at 10. Alright, so this graph goes something like this. Hopefully you have a smoother curve than mine turned out to be. It's sort of like an arc, like that. Alright, so forgive the shaky drawing, but I'm sure yours is a smooth curve. And what we're going to do now is create our boxes. Alright, so we have these rectangles. They're going to be right rectangles. So I get the height of each one by the point on the right. So the height of the first one, I look at the right side and I make the box like that. Here's the right side of the next one. Here's the right side. And right side, and right side. On this curve, you see our approximation is going to be a little higher than the actual area under the curve. When it says find distance, if we have feet per second on this axis and seconds on this axis, remember the area under the curve is going to be feet per second times seconds. So the area under the curve does give us the distance in feet. So we're embarking on the right method here. All right, let's gather these numbers. We've got this box is, we know at 2 that the function had a value of 6. Well, we know 0, 0. That's just going to be a 0. So then we're going to add, well, no, 0 is not involved. This is a right box, I'm sorry. So at 2 seconds, we know the width of each of our boxes is 2, and the height of the first one is 6. So I took care of that box. The next box has a right value of 7.5 and a width of 2. The next one is 2, and its height is 8.5. 2, a width of 2, and the next box is a 9, plus 2, The next box is a 9.5, and 2, and the next box is a 10. So if I write all that out and calculate it, go ahead and see what you get. And I would tell you, I haven't shown you this or discussed it, you probably saw it for yourself. A lot of times what I do is I pull out the 2 in front and just add these numbers. It just saves me a couple keystrokes. So if there's a 2 in every one of those, I go ahead and add up all of these and then multiply the entire sum by 2. And it will get me this sum a little more quickly. Alright, when I did that, I got an area of approximately, and this area happens to be distance, 101 feet. Did you get that as well? Alright, hopefully you did. So notice how it was quite simple, even though we didn't know the name of the function, it was quite simple to get the heights of each of these boxes right from our chart. So I'll be asking you to do another one of those later, so keep that in mind. Alright, our next point for discussion is a new method of finding areas under the curves. We've done the right boxes, we've done the left boxes, we did the midpoint boxes, and now we're going to do another kind of box. So I need to erase this, so dramatic pause for a second. I forgot to get my paper towel. Alright, here we go. Next one. We're going to have our graceful curve like this. Alright, this is my feel-good curve, and I'm going to create some areas like we did like yesterday when we're doing the general forms. We had an A and we had a B. And in between we'll put in some boxes. I'll put 3 on this side and 2 on this side and lots of boxes in between. And we call this x naught, x sub 0, x sub 1, x sub 2, x sub 3. This one was x sub n, and this one was x sub n minus 1. And if I had room or wanted to, this would be x sub n minus 2. So set that up like we did yesterday. And I'm not using right side, left side, or midpoint boxes, but I'm going to take the point that is the top of that line on the function and the point on top of that line on the function and connect them with a straight line. So what is the shape that I've created here? So I'll actually lift that shape up here. It looks something like that. Notice it has 2 sides parallel and 2 sides that are not parallel. So that is the name of a trapezoid. Alright. The trapezoid has a height that is the distance between the 2 bases. So actually the distance between these 2 long parallel lines is the height, and the area of the trapezoid is the height times the sum of the bases, base 1 plus base 2, divided by 2. So it's actually the average of the bases times the height. So the bases are going to be these sides of what was a rectangle. So this is base 1 and this is base 2. So with that in mind, let's see if we can come up with a general formula for our trapezoidal method. So we're going to find that the area equals approximately we're going to add And the first one, we're going to take the height, which is change of x. And we already know from previous times that it's b minus a divided by the number of boxes. But we're not going to write that every time. We'll just call it change of x. Then we're going to put in this area right here. We're going to put in this term right here. So base 1 is this line. It's connected to this line. So it's the function of x at x sub o. And also we are going to add the base right here plus x sub 1 and divide it in half. So we're going to take the f of x sub o and add it to f of x sub 1. I wrote that wrong. Let me clarify. So we're going to take the function at x sub o and we are going to add to it the function evaluated at x sub 1 and divide that by 2. And that will get us the first box right there. Then we're going to do that again for the next box. I'm just going to put dot 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 and say it out loud, not write it. The next box will be change of x times the function evaluated at x sub 1 plus the function evaluated at x sub 2. And that will be added, those two will be added together and that cut in half. Alright, so we'll do that over and over as we go. So let's make a general term for that using our summation notation. So we have A equals the summation of change of x. And now I'm going to take the function of, and I can put x sub 1, the summation, I forgot the summation sign. Let me put that in here. Sorry about that. Hope your erasers are handy or that you're slow writers. All right. The summation as I goes from 1 to n. And we have change of x for our width. And now we need to add the bases and divide by 2. So I'm going to go function of, if I want f sub 0 and I start it with 1, I'm going to have to go f of I minus 1. And then I'm going to add to that the function of x sub I and divide all that by 2. So there we have the general expression that will give us all of these boxes. All right, let's do a particular problem that exemplifies that. So get that down, and we'll go ahead and talk about one problem, and then I'll assign you, say, 4 of these to do. That sounds like a reasonable amount to me. So let me go ahead and, I always forgot to time this video. Hopefully I have time to do let me go ahead and actually shut down this video and have you call up the next video so that I don't go over my limit. It gets hard to upload when I do. So just be right back.